All right, so we're looking at 2.1 basics of functions. And I already had these notes, majority of these notes in another class, so I'm going there. All right, so we're going to start off with defining what a relation is. A relation is any set of ordered pairs. And don't forget your ordered pairs are made up of your x and y component. An example of that is 1, 2, 3, 4, and 5, 6. Right? Your domain is a set of all of your first components of the ordered pairs. So from this example, 1, 3, and 5 will be your domain. And your range would be the set of all of your second components of the ordered pairs, which from this example would be 2, 4, 6. All right. Of course, if I were to scroll up and you're not finished, let me know. I can't see who's writing, who's not, or who's finished and who's not. So always remember to let me know. So comparison between your domain and range. As mentioned before, domain is your first components, range is your second components. That means your domain will be your x variables, range will be your y variables. Domain also is your input versus your range being your output. Your domain will be your independent variable, range your dependent variable, and your domain's your horizontal axis, while your range will be your vertical axis. So just in case there's not an x and y and there's a s and t, a m or n, and all that good stuff like that, those are the characteristics of your domain and range. All right. All right, so the definition of a function. A function is a relation in which the elements from the domain corresponds to exactly one element in the range. So the elements in your range correspond to exactly one element in your range. All right. So directions determine whether each relation is a function. All right, let me erase some of this stuff so we can walk through it. All right, so this first one, we have 1, 6, 2, 6, 3, 8, 4, 9. All right, and so one way to do this is to create a mapping of what goes from the domain to the range. So what's in our domain is 1, 2, 3, and 4. Our range has 6, 8, 9. All right, so it is best to make sure we look at each element individually and not look at them as a set in order to be able to define whether we have a function or not. So remember, each element in your domain has to go to one element in your range. So when you do your mapping, does one go to exactly one element, which is 6? The answer is yes. We have to be able to answer yes to each one of the elements in the domain. Does 2 go to exactly one element? The answer is yes. Now, it may go to the same one that 1 goes to. That's fine. that does not stop it from being a function. What stops it from being a function is that your elements in your domain go to more than one element. So does one go to one element? Yes. Does two go to one element? Yes. Does three go to one element? Yes. Does four go to one element? Yes. Since I can answer yes for all four of those, that means yes, it is a function. All right. Questions before we look at the next one? All right. That's not what we need. Or somebody asking the question. All right. So here, let me, like I said, let's walk through it. So we have 61218394. So 689 is in our domain. 1, 2, 3, 4 is in the range. So once again, we're going to start off with each individual domain element. So 6 goes to 1, and then 6 goes to 2. So I don't have to evaluate the rest of them. 6 going to more than one value is a problem. So no, it is not a function. So can't have your elements in your domain going to more than one value.
Hey, sir, I have a question.
Mm-hmm.
So if it was the opposite, though, it would be okay?
Yes.
The one before that?
Right.
Okay.
Mm-hmm. And so when we talk about the generalization, I got two general statements that we could, they're pretty much attacks what you're saying right there. I'm gonna let them finish copying this and then I'll scroll down.
All right. Thanks, sir.
Yeah, no problem. All right. So scrolling down. So to address what your classmate just mentioned, there can be a repeated value in the range, but no value can repeat in the domain. So if you go back to what our last two examples, we had the repeated value of 6 in the range. That was okay to be a function, but then we had a repeated value of 6 in the domain, so that stopped it from being a function. So there can be a repeated value in the range, but no value can repeat in the domain. And then also the range can go to more than one value. The domain can go to only one value. All right, any questions before we do another one? All right, so let's go back to 62. And this what's in red right here is just a note to myself, so it's not for you guys. All right. So let's go here, determine. Whether each, sorry about that, right? Each equation. All right, so determine whether each equation defines y as a function of x. So we're doing it algebraically. First, we're going to solve our equation for y. Ah. So subtract x squared from both sides. Y is equal to 4 minus x squared. And then here, let's see how I want to say this, repeated. All right, so somebody said something in the chat. Can you scroll back up? All right, so yeah, there was nothing up there, so this is where it starts for this set of notes. Okay. All right. So we're going to take that equation, solve it for y. And then once we do that, we're going to evaluate the equation to see if a repeated y value can be produced. And I'll show you what I mean when we get to plug in. And you'll see when we do the next example, you'll really see the difference in between the two equations, and what would actually give you a scenario that's not a function versus what scenario would produce a function. So create an XY chart. Yeah, I can plug in -1. All right, so I'm just choosing some x values to see the nature of the function that I have. So when I plug in +1 into my equation, that's 4 minus 1, which is 3. When I plug in -1 into the equation, that's 4 minus 1, which is still 3. I shouldn't say repeated. Change that. Let's see. Change that repeated to multiple. There you go. I said repeat. I shouldn't have said repeated. So you want to evaluate to see if multiple y values can be reproduced. Right. Multiple y values. And I'll show you what I mean in a second. So then plug into you get 4 minus 4, which is 0. So before we analyze our chart, and so I can show you what I mean, questions on what I did. I chose 3x values, plug them into the equation, and got out their corresponding y values. So when you plug in an x value, you're only getting out one y value. Each x value produces just one y value. In this case, that's the only scenario that can be created. You can only produce one y value when you plug in an x value. Like I said, when you look at the next one, you'll see how that can be done, how it can be produced, or how an x value can produce more than one y value. But as of right now, this one can, when we're looking at this example, this one cannot produce anything but one y value per x value that you plug in. And because that is the case, this is a function. So every time you plug in an x value, you will get just one y value. All right, looking at the next one. X squared plus y squared equal to 4. So what's the difference between, or the main difference between this one and the last one? We have an even root on the y. So what is that going to do for us? The first step is to still solve it for solve it for y, excuse me. So we got x squared plus y squared equal to 4. I'm going to subtract x squared. Y squared equal to 4 minus x squared. Don't forget square root property. Because remember, we're solving for y. If you take the square root of both sides, that's going to be y equal to plus or minus square root of 4 minus x squared. All right. Don't forget, whenever you take the square root of both sides, you have to use plus or minus. And for any even root, that will be the case. All right. So now, once I solve my equation for y, I do like I did before and set up my xy chart. And if I plug in 1, I'll go 1. Yeah. If I let x be equal to 1, plus or minus 4 minus 1, plus or minus square root of 3. All right. So this means that when I plug in 1, I get out positive square root of 3 and negative square root of 3. I get out 2 values. So basically, we go back to our mapping, how we did our mapping before. If I had 1 in here in my range, and then in my, 1 in my domain, then 1 in square root of 3 and positive square root of 3 in my range, the 1 would go to both of those values. And remember, that's what we cannot have. So All right, so x produced two y values. So this is not a function. All right, questions on that before we go any further? So once again, that main deciding factor on whether this was a function or not was having this even root on, or even power. I should say even power on your y, because what you're going to do is take an even root to both sides. So that even number right here will produce this double value. All right. Let's look at vertical line test. All right. Making sure that my thing is straight. Hold up. Okay, there we go. So vertical line test. If any vertical line crosses or touches a graph more than once, it is not a function. So if we had a circle, so just a circle touches it twice when you draw a vertical line through it, so not a function. Linear equation, no matter where you draw a vertical line, it's only going to touch it once. So yes, it is a function. Parabola, no matter where you draw your vertical line, it's only going to touch it once. So yes, it is a function. And then here, even though I may only touch it once right here, when I get here, touches it 3 times, so that means no, it's not a function. So if you take a vertical line and draw it through your graph, and it touches your graph or crosses your graph more than once, then it is not a function. Questions? Any questions? All right. Okay, here we go. So one last thing out of this section, function notation. All right, so function notation, y is equal to f of x. So wherever you see y, you can plug in f of x, and they will assume that you know that that is the case. They are interchangeable. You can switch them back and forth within one problem explanation, and they would expect you to know what they're doing and what's going on. Y and f of x are interchangeable. So y is equal to 2x plus 1. That means f of x is equal to 2x plus 1. That is in function notation once you do that. And that's, you know, seen it. That is called f of x. That's how you say that. It's like if you had gt, that would be g of t, you know, s of r, and so on. All right. All right. So if I have, what this enables us to do is give instructions without actually giving words. I didn't even have to put find right here if I didn't want to. If you want to know what f of 3 was, you would take your f function and plug 3 into it. And so that's all that means, is that if you want to find f of 3, notice the 3 is substituted for x right here. So that means you're going to take 3 and plug it into your equation where you see an x. That'd be 6 plus 1. That'd be 7. So f of 3 is 7. That also means your ordered pair is 3, 7. 3 is what you plug in. 7 is what you got out. 3 is your domain. 3 is in your domain. 7 is in your range, and so on. All right, so here, and they have to define what your function is, of course, before you can know what to plug into what. It says find, it says if f of x equal to x squared plus 3x plus 5, find or evaluate f of 2, and then f of x plus 3. So f of 2 means you will take 2, plug it in where you see x. Then calculate 2 squared is 4, 3 times 2 is 6, plus 5, 4 plus 6 plus 5 is 15. All right. Any questions on that one? All right. Do the same for the next one, except we're going to plug in the quantity of x plus 3. So that would be x plus 3 squared plus 3 times x plus 3 plus 5. All right, so don't forget x plus 3 squared is x plus 3 times x plus 3. X squared, 3x. So don't forget you're doing your binomial distribution. X times x is x squared. X times 3 is 3x. 3 times x is 3x. And then 3 times 3 in the back is 9. Combine your like terms. And we're looking at x squared plus 6x plus 9. Distribute your 3. And that plus 5 is still back there. All right, combine your like terms. 6x plus 3x is 9x. Then we have 9 plus 9, which is 18, plus 3, 23. All right, questions on anything said so far? This class is in. Okay, we can start 2.2. Oh, she's not asked question. You're not factor? No, you don't have to factor. There's nothing else you can do with that. Even if you could factor, there's no purpose because you can't reduce it or anything like that. So that's all they need from you out of this problem. Good question. Good question. So we'll at least get started on 2.2, see where it takes us. Okay. Right there better. I want to say x as x value increases. Yeah, I can get there. All right, so we have 3 of them, increasing, decreasing, and constant. Just want to read through this before we write the constant. Increasing on an open interval, as x value increases, the y value increases. So reading from left to right, your graph goes up. Decreasing, your function decreases on an open interval, as the x value increases, the y value decreases. So your graph goes down, reading it from left to right. All right, so constant on an open interval to me, as x value increases, the y value stays the same. In other words, constant. All right. Mm-mm-mm. All right, so looking at the first one, it says state the intervals on which each is increasing, decreasing, or constant. All right, so when we write these intervals, we want to use the x values. So we're not establishing our intervals according to what the y is, just according to what x is. So when I look at this first interval, this right here, and I probably should have went purple, a little brighter, more distinct. So this is my first interval or change. And reading it from left to right, I'm going up. So I'm coming from negative infinity to -2. All right, this is that right here where it stops, x-wise, as far as x is concerned. So I'm coming from negative infinity to -2. All right, then from -2 to 2, it's constant. And then from 2 down to, well, 2 to infinity, 2 to positive infinity. Remember, we're not going down, we're going to the right. So we're going to be looking at our x values. 2 to infinity is decreasing. Questions on that one before we do another one? Oh, I messed that up. All right, so we'll look at this next one. Once again, we want to know, is it increasing, decreasing, or constant? All right, so our first interval comes from negative infinity to 0, and it's going down. So that's decreasing. Then I'm going up from 0 to 2. So that's increasing from 0 to 2. Then I'm going back down from 2 to positive infinity. So if we have more than one, and that's decreasing. So if we have more than one interval that's in one category, we use a union sign, and that'll be 2 to infinity. And that would be none for constant. All right, questions
Yes,
on that?
yes, sir. Could you explain the decreasing part of B again on the whole union thing?
Oh, that's just a symbol, the symbol that you would use.
So,
If you have more than one interval that fits the description of decreasing, or if I had another interval that fits the description of increasing, if I wanted to put another interval here, I would have to use the union sign and then
okay.
forward or whatever, whatever that interval is. So that
Okay.
union sign is just a part of your notation.
All right. Thank you.
Yep, no problem. And then once again, just to make sure everybody's clear, that union sign is not just, and I may have said it that way, so that's why I'm doubling back. That union sign is not just for decreasing or any one category. Whenever you have more than one symbol, more than one interval that fits a characteristic, or you want to use, let's say as a solution set, you use that union sign. So if I'm going 1 to 2, 3 to 5, 10 to infinity, I always have to use the union signs. They represent or. So it's this or this or this. Um, yep, that's our union symbol. So what I'm saying is that what you can't do is, what you're not supposed to do is just put a comma there or something like that, or just leave it like that. You have to put that union symbol there. All right. Let's look at let me see. I don't think the A is supposed to be there. Hold on. Come on, man, erase. There we go. I'll say open interval. All right. All right. So, relative extrema. We were talking about the relative maximum and relative minimum. So, the relative maximum will be the maximum value or the largest value relative to an open interval. So, if you have your interval, the largest value there in that interval would be your relative max. And your relative minimum would be the largest or smallest value or the minimum value relative to an open interval. So if you have an interval, the smallest value in that interval would be your relative minimum. And just a generic example, if I have this shape or this graph, notice that there is not a maximum or a minimum because it goes on to infinity in this direction, which would cancel out any max you have because that's infinity. And then it goes on to infinity in this direction. So that will mess you up as far as finding a smallest value possible. So what you can do is have your interval, and you see right here, this hill right here could be considered your relative max. That's the largest value, let's say from this value to this value, that interval. And then here, that could be your relative minimum, or the lowest value within that interval. So they would be dependent upon what your interval is, and the smallest value or the largest value between two sets of numbers. So let me see. Don't see any examples. Okay, so this exercise basically tell you to use your calculator and a graphing tool to find your relative extreme. So there may be something that I will have to address to each one of you individually according to the calculator or your tool that you have. Let me see. Graph the function, use the graph. Let me see. What I'll do is, do I want to do this next class? What time is it? One thing, no, I got time. This is what I'll do. Next class, I will pull out a graphing tool and just show you how to do it. Try to find something reliable online so I can switch to instead of trying to find something this time. I thought it would give me an example, but they really just want you to use a graphing tool in order to be able to find your relative min, relative max. So next class, I'll take time out, find a graphing tool and write that note to myself. And we'll look at that. All right, so we'll do that next class. All right, so we got 15 minutes. Let's touch on symmetry, and then I'll let you guys go. All right, so definition of symmetry. The first one is symmetric with respect to the y-axis. For every point on the graph, the point negative x, y is also on the graph. So the way we'll test for this symmetry is to substitute negative x for x in the equation, and the result should be the same equation that we started off with. All right. So we got symmetric to the y-axis. We also have symmetric to the x-axis, and then symmetric to with respect to the origin. So we have three of them all together. What in the world? Sorry about that. I got kicked out of my notes for some reason. All right, symmetric with respect to the x-axis for every point on the graph. The point x negative y is also on the graph. So to test that symmetry, we would substitute negative y for y in the equation, and that results in an equivalent equation. All right, so symmetric with respect to the origin. For every point on the graph, the point negative x, negative y is also on the graph. So to test this for symmetry, we're going to substitute in negative x for x, negative y for y, and the result should be an equivalent equation. All right, so let's try it out. So you want to determine whether the graph of x equal to y squared minus 1 is symmetric to the y-axis, x-axis, or the origin. I won't say let. All right, so let's look at the first one. If we want to test for symmetry with respect to the y-axis, we're going to substitute in negative x for x and see if we have an equivalent equation. Or in other words, does it give us the original equation? This is our original equation. If I plug in negative x for x, after I simplify, if it gives me back what I originally had, that means it is symmetric about the y-axis, or symmetric with it with respect to the y-axis. So that means I'm plugging in negative x here equal to y squared minus 1. So what I would do is, because I have x equal to y squared minus 1 in my original equation, I want to have x equal to, and then I'd be able to make a clean comparison. So I will multiply both sides by -1, since I want to get that negative off of my x. This is x equal to negative y squared plus 1. All right. All right, so since this is not the original equation, or the original equation was x equal to y squared minus 1, this is x equal to negative y squared plus 1. So since this is not the original equation, the function is not symmetric about the y-axis. Also, I say about the y-axis, all you can say with respect to the y-axis, both of those. All right, so well, we got 2 minutes left. I'll pause here. So we'll pick up right here on next class. Next class ends at 1:45. Yep. So we will pick up right here on next class, finish the rest of the section, and go from there. Questions, concerns, or comments before we close out? Everybody good? Everybody straight? All right. So take care. Have a good one. Once again, we'll pick up right here on next class, and see you Wednesday.